Okay, so in this part of the module, we'll talk about distribution. So what happens after the drug is taken up in the blood circulation, how it's distributed to the site of action and to other body tissues and organs that are not necessarily where we want the drug to go. So in other words, the bloodstream will take the drug throughout the body, distributing it to the intended site of action and then to other organs. The distribution to other body tissues and organs, other than the site of action intended, have the net effect of diluting the drug. In other words, in an ideal situation, we'll have the distribution of the drug exclusively and specifically to the site of action. That will maintain a higher concentration of the drug at the site of action and also will decrease side effects, because when a drug is distributed to other tissues and organs, we can have possible side effects. So how do we look at the distribution and how we try to make some sense of the relationship between the concentration of a drug in the bloodstream and in the tissues? So what we do is we call this parameter volume of distribution. And this is actually the apparent volume of distribution. In general, VD is the volume of water necessary to hold the administered drug at a measured concentration in the blood, right? And so what we have is given by the ratio of the amount of drug in the body at equilibrium over the plasma concentration. For example, the volume distribution relies on one only quantity that is actually measured, and that is the concentration of the drug in the plasma. So, in general words, and I know this is a kind of complicated to put in place, the volume distribution is the amount of water necessary to hold the administered drug at a measured concentration in blood. So let's say we have a drug for which we give 100 milligrams, and let's say that at equilibrium, the concentration of this drug is 10 milligrams per liter. And remember, here we have a practical problem, so the only thing that we can measure after the drug has been administered is its concentration in the plasma. That can be done very easily. So the volume distribution here is going to be given by the amount of drug we have given over the concentration, 10 milliliter, and so it will be 10 liter. In other words, we will need 10 liters of water to dilute the overall dose of the drug until the concentration is 10 mg per liter. So what that tells us is that this helps us thinking that the drug is distributed in a volume at a constant concentration. And so if the concentration of the drug in the rest of the body was the same as in the plasma, the body volume will have to be 10 liters. So what's the meaning of VD? And I know this is a little bit tricky to conceptualize, but it's related to the fact that a drug will be found in mainly in the body fluids. And so in a typical and standard person weighing 70 kilos, which is about 150 pounds, give and take, we have that 33% of the body weight, so in other words, 23 liters in this case, will be water. Extracellular water, so water that is found in the tissues within cells, is about 19 liters. Plasma water, so the water in the bloodstream, is about 3.2 liters. Water in the interstitials, again, between tissues, and transcellular water are only about a smaller fraction. So when the volume distribution is equal to the volume of the plasma, then we will have a drug such as destrain that is only distributed in the bloodstream and is not taken up by any tissues. The volume distribution will be equal to the body water for a drug that is distributed equally to all the aqueous compartments. And then the volume distribution will be larger than the total body water for drugs that are actually accumulating in tissues. And a typical example of that is fat tissues, where certain lipophilic drugs such as hormones, but also drugs that act on the central nervous system accumulate. And so they basically slowly equilibrate with the bloodstream, so they're accumulating in the fat tissues, and then from the fat tissues they're slowly released. So what I want you to remember for volume distribution is basically this quantity here, and that gives you an idea of the fate of the drug in the body. So let's think about it for a little bit again with our standard male that weighs about 70 kilograms, so 150 pounds. So let's say that the body is not what we have depicted here, but is represented or approximated by a bathtub. And in that bathtub, we'll have about 40 liters of water. 40 liters of water will be corresponding to these quantities. And so now we're going to throw in, a certain amount of drug, and let's say we put, 200 milligrams of a drug, and we'll measure the concentration of the drug in the bathtub once it's completely dissolved. And what we'll find is that, that's going to be 200 over 40 liters, and so it will be about 5 milligrams per liter. That's the overall concentration. So what this quantity tells us now, in other words, is also that the drug was distributed equally towards throughout the whole water tub. And so if the volume distribution is 40 liters, then we know that the drug is distributed completely into all the tissues in the body, all the water compartments in the body. The other quantity that determines how well a drug makes it to the tissues is looking at the blood perfusion rate. In other words, how rapidly does the blood go through certain tissues. And so this is measured by the so-called perfusion rate, which is milligrams of blood per minute over 100 grams of tissues. The most rapidly aerated tissues are the lungs. And that makes sense because in the lung, basically the blood gets oxygenated, and so oxygen is basically incorporated in hemoglobin, and then from that is distributed to the rest of the organism. The second more rapidly perfused organ is the kidney. Kidney is in charge of filtering the bloodstream, and so in other words, it's in charge of eliminating toxic compounds from the bloodstream. The third, more related, basically at the same level, are liver and heart. Again, liver is in charge of detoxifying the bloodstream, and so taking up and eliminating chemical compounds that are found in the bloodstream. And the heart also is, well, all the blood has to go through the heart in order to be distributed to the other organs. And also the heart needs to be maintained with a very high metabolism, which is why the aeration rate, the perfusion rate needs to be high. Same for the brain. Muscle, skins, and fat basically are perfused at a much lower rate. The other quantity that will determine how well the drug is distributed to the organism is binding to plasma proteins. So in general, drugs are bound to plasma proteins in the bloodstream. They're not just solubilized in the plasma. Several of these proteins, we have basically albumin, seroalbumin, and other glycoproteins and lipoproteins that are in charge of distributing compounds such as hormones throughout the body. These are also the target of binding for many drugs. For example, warfarin, which is an anticoagulant drug, binds with very high affinity to human serum albumin. And when it does that, influences the equilibrium between the bloodstreams and the tissues. And so we have a reservoir of warfarin stored into these plasma proteins. And that will also change the volume distribution. So the volume distribution for warfarin is 9.8, and that implies that the drug is not distributed to the tissues, but it's also larger than the quantity, the amount of plasma that we have in our individual. And so that indicates that the concentration is higher than what we would find if it were simply solubilized. It's about 3 times higher than what we will expect. The difference is made up by the drug that is bound to the plasma protein. So now let's look at volume of distribution for certain drugs. And so we are comparing several of these drugs. And what we can also note is that whether a drug is basic or acid will influence its distribution, this volume of distribution. In general, drugs that are basic tend to distribute to a larger volume, so they tend to accumulate in tissues. That is again due to the partitioning into the So what we find is that in general, drugs that are basic in nature partition to tissues much better than drugs that are acidic in nature. And so the volume distribution of a drug such as salicylic acid, which is water soluble and mildly acidic, is higher than the volume distribution of a drug that is lipophilic and mildly basic. We can also look at the accumulation of certain drugs. So thiopental, which we saw has a log P of 2.7, so it's a very lipophilic drug, tends to accumulate in adipose tissues because it's lipophilic. And so if we look at what happens to an initial dose of 100% of the dose over time, and we look at the distribution in various tissues, we'll find that from the bloodstream, the concentration in the plasma goes down very rapidly. At the same time, we have an increase of the concentration of the drug in the brain, right? Which is great because that's our intended tissues, site of distribution for this drug, which acts on the central nervous system. From the brain, then, the drug is redistributed through the plasma back to muscles, and then eventually finds itself to the fat tissues where it tends to accumulate for a very long time, and so for several days. From the fat tissues, in turn, thiopental is distributed back to the bloodstream and back to the brain and then excreted. All these factors are, as we said, influenced by pH, and specifically they are influenced also by whether a drug is ionized or non-ionized in a particular compartment. For example, let's look at what happens to a weak acid that is now, finds itself in the gastric juice, in the plasma, and the urine, and how does it get trapped and therefore distributed to various tissues. So we already saw that given the pKa of our drug, and let's assume the pKa is 4, so that's the number we are using for our hypothetical drug. In the gastric juice, the drug is primarily non-ionized, and so will be absorbed in the stomach. So here we have absorption. From there, it is taken up in the plasma. And now in the plasma, the pH is about 7, so drug re-equilibrates, and we find that, only a small quantity of the drug is present in the non-ionized form. Most of it will be present as an anion, and therefore, from the plasma, it will not distribute very rapidly to the tissues. Finally, the drug will be distributed to the urines in the kidney, and we'll see how the excretion functions. And so here the pH is basic, it's about 8. And so now the vast majority of the drug will find itself in the ionized form, and it thus will not be reabsorbed in the urines, but rather will be excreted. This concept is called ion trapping, and so basically what tells us is that a drug will go through several compartments, and then based on the pH in the specific compartment, in this case we are comparing liquid compartments, it will find itself trapped in one form or in another. What we have seen here is that in the gastric juice, the weak acid is non-ionized and therefore will be distributed very rapidly and absorbed. As we go through the plasma, the drug becomes more ionized and therefore will distribute more slowly, and there will be an equilibrium of distribution to the tissues. Once the drug makes it to the urine, will be completely or almost completely ionized, so we'll have 10,000, the concentration of the drug will be 10,000 higher than the concentration of the non-ionized drug, and therefore the drug will be rapidly excreted and eliminated in the urines. For weak bases, the situation is opposite. So in the gastric juice, where pH is acid, the drug will be found mainly into this ionic form, and therefore only a very small part is absorbed in the stomach. And as we saw weak bases tend to be absorbed mainly in the intestine. Once the drug is in the plasma, though, we'll find, once again, pH 7, only 1/1,000 of the drug will be available for absorption and distribution to the tissues. However, once the drug makes it to the urine compartment, we'll see that, in this case, we'll have 1/100 for the concentration of drug that can be distributed. And so elimination of weak bases tend to be more difficult than elimination of weak acid. All these factors come together to influence what we call the therapeutic windows. In designing a drug, we want to maximize the concentration of the drug that is effective in the plasma. In other words, we want to make sure that the plasma concentration is in the range that is responsible for activity. And so we can think of it as a graph where we correlate plasma concentration with time. And we'll have two levels. One is the so-called minimally effective concentration. So when the concentration of the drug in the plasma falls below that level, the drug becomes inactive. So we are out of the so-called therapeutic window. On the other extreme, if the concentration of the drug goes up too much in the bloodstream, what we find is that we are at toxic level, so where we start having important side effects, and so the drug is not useful anymore because it causes more damage than what it will cure. And in general, because of all these factors of distribution and, as we'll see, also metabolism that happens, the concentration of the drug will go up after administration to a certain maximum, and then will go down. And during this curve, we'll have excretion and metabolism. Metabolism is the series of reactions that happen on a drug and basically alter its scaffold so that the drug is not effective anymore. So because of these factors, the concentration of drug in the plasma will go down to until a certain minimum level, at which we administer another dose of the drug, and we start again with this curve. In general, so our purpose when administering a drug is to keep the concentration in the plasma in the therapeutic window. We don't want to overshoot. We don't want the drug to be absorbed too rapidly and basically reach a very high concentration in the plasma. And we don't want the drug to be eliminated too rapidly, and we want to maximize, again, the therapeutic window.